All right, so we're going to think about which one of these 5 molecules has the highest boiling point. Notice that their molar masses are all given just below their molecular structure. They're all approximately the same molar mass, so the differences in boiling points should arise due to differences in intermolecular forces between molecules of each type. So let's think about different types of molecules and what their strongest intermolecular forces of attraction might be. So we'll take H2S first. H2S has a structure given here that in three-dimensional geometry might look something like this. It's a bent molecular geometry, therefore it contains poles of partial negative charge and partial positive charge. And the hydrogen side is the partial positive end of the molecule. Overall, our molecule must have some polar interaction, and the strongest intermolecular force of interaction that it could contain, because of this central sulfur atom, is a dipole-dipole. So what about the other molecules? We'll think about H3P next. If we draw molecular geometry for H3P, we have a partial negative charge on the central phosphorus and a partial positive charge on the hydrogens that sit down below. This molecule's strongest intermolecular force of interaction must also be dipole-dipole. For SiH4, a central silicon atom with 4 hydrogens, is completely symmetric and therefore must be nonpolar. This is a tetrahedral molecule. Nonpolar molecules' strongest intermolecular force of interaction can only be London dispersion forces. For CH3F, we again have a tetrahedral molecule, a central carbon atom with 3 hydrogens bound to it, and a fluorine off to one side. While this is a tetrahedral molecule like silane SiH4, it is not completely symmetrical because the fluorine on this side is different from the hydrogens on the other sides. That means that this is a polar molecule. We have a partial negative charge on the fluorine side and a partial positive charge over on the hydrogen side. The strongest intermolecular forces of interaction between molecules of fluoromethane must be dipole-dipole. All right, so lastly, methanol. A central carbon atom with bonds to 3 hydrogens, and oxygen off to one side that's got a bond to a hydrogen itself. This is a more complex molecule than any of the others before. We have 2 centers of geometry. We have this carbon, which is tetrahedral, and we have this oxygen, which is bent. So, in reality, we have got several areas of electron distribution bias. This oxygen is partially negatively charged, whereas this hydrogen is partially positively charged. This oxygen is partially negatively charged, and this whole side of our molecule has a lack of electron density, as electrons are being funneled towards that oxygen who's really electronegative and really greedy. So we do have dipole moments in this molecule of methanol, but we have a special case for dipole moments. This special case arises from a hydrogen bound to an oxygen. And anytime hydrogen is bound to oxygen, nitrogen, or fluorine, the 3 most electronegative atoms from the periodic table, we'll say that hydrogen is so biased in terms of the electron density that sits around it that it's an even stronger case of dipole-dipole attraction called hydrogen bonding. this isn't true bonding, but rather an intermolecular force of attraction between molecules that contain a hydrogen bound to oxygen, nitrogen, or fluorine. So, overall, we can rank the general forces associated with molecules of each type. We can say that silane represents a very weak intermolecular force of attraction, whereas methanol represents the strongest of this group in terms of intermolecular forces. The other molecules are somewhere in between. Remember that hydrogen bonding is a stronger intermolecular force than general dipole-dipoles alone. So, which of these molecules has the highest boiling point? In other words, for which of these molecules will it be most difficult to pull apart? The most difficult molecules to pull apart from each other will be the molecules with the strongest forces of intermolecular attraction. So, methanol must have the highest boiling point.